Well, many of you were excited to see our Chernobyl reactor computer in action. And I have to say, this escalated quickly, because we built this. I honestly don't know if it is still retro computing or already something far different. Welcome back. So, last week we took a good look at our Chernobyl SKALA computer simulator, and we have a rather unexpected upgrade. If you are the first time here, SKALA was a system that analyzed thousands of parameters of a nuclear reactor and assisted its operators. It works with a system of codes and natively gives responses on special displays. It was something similar to Apollo guidance computer. Honestly, it was a great fun to build it, and today I will show you how we made it step by step. But to unleash its full potential, it is missing this display. We are now building it as well, and I even got a simple CNC machine to make 2,000 of those squares that will light up. But as many of you wanted to see the magic SKALA can do with it, I spent one evening and programmed a digital version fully integrated with the console. And today I will also show you how to do some tricks on this screen. You may ask, why CRT display? Well, because it was inspired by DE's 2000 upgrade system from the 90s we previously had a video about. So, responses of SKALA computer are presented on special display sets, and they look like this. They receive a quite complex data code, unpack it and show either 5 or 7 characters. That can be codes, numbers, set points, symbols, basically whatever you may need. And as you know, we love to stay as close to original tech as possible, so we made blueprints of the front panels and then 3D printed them. Next, we laser cut green filters and masks and secured them inside the housings. Well, obviously with today's technology we can make electronic parts much more compact, but what we really wanted to do is to use VFD indicators, same as in original, because they glow beautiful turquoise color. And this is when I made a big discovery. For digits they used very common If22 tubes, which you can find basically in any kind of Soviet equipment. But tubes for letters and symbols are something else. Those are experimental P422, manufactured by the Reflector factory in Saratov in Russia. And those are such unicorns that there are no references of them in literature and there are no even pictures of them. Anyway, it looks like the choice of P422 was a problem from the very beginning, because in schematics later they were changed to P418. The only problem is those P418 were experimental as well. There were just 2 pictures of them on the internet, not even saying that you absolutely cannot buy them. How did the nuclear power plant used to deal with repairs and replacements? Well, I have absolutely no idea. And that's why we instead used green LED matrices. They are controlled by chains of shift registers, which are connected to a few ESP Mini. Each acts as a character generator for 2 complete displays, and all that sits on one shared I2C bus. So entire assembly needs just 2 data lines in addition to power. At the moment these modules are installed on this metal panel. That was rather a temporary solution we made for the exhibition dedicated to 40th anniversary of Chernobyl disaster. There this panel was mounted beneath the mnemonic diagram of SKALA. So later we will rebuild this part properly and more compact, something like this. Still, this was nothing compared to building the keyboards. The entire process may appear pretty illogical, but that's because of the order the components are mounted and connected. And so we begin with the most exciting part, the switches. And we have a rather unexpected upgrade. You see, the keyboards use the infamous Soviet P2K switches. Infamous because they are notoriously unreliable. And with our luck, SKALA uses a rare version, with 8 interlocking buttons. I searched everywhere and managed to find only 1 complete original assembly on sale, and so out of options I decided to make the others myself. And so I bought a large number of independent switches with the correct spacing and another group of interlocking switches with the wrong spacing. And then to convert one into another, you basically need to swap everything and add a rail like this. Of course, you cannot buy them anywhere, so we had to measure the original part, make some technical drawings and laser cut them. This is how many we made, just in the case. Then came the truly enjoyable part. I had to disassemble every switch block into its smallest components. That meant bending open the fasteners, removing the retainers and springs, and constantly watching so these tiny contacts inside didn't fall out. Then I installed the correct switches into new rails and assembled everything again, and I repeated the process a few hundred of times. Remarkable. Well, the result actually worked, but unfortunately sometimes everything jammed. And that was one of those very rare moments when I had to admit that historical accuracy has limits. And so I kept only 2 original assemblies that have a fewer buttons, and for the main code panels I've got modern versions. The next step was making the button caps. As before, we asked our contractor to engrave every letter and number using a CNC, so it matches the original look. Let's say the job was that difficult that after finishing it, they very politely asked us never to order anything like this ever again. Then I filled the markings with paint. Well, you may remember I used a similar method while building the reactor control panel. Basically, you pick a drop of paint on a syringe and make a few smears. Then you leave all buttons to dry for about 10 minutes, and it's quite important not to let it dry completely. Then you take soft paper, soak it in solvent, and carefully wipe the excess paint from the surface, so it remains only inside the engraved symbols. This operation I repeated more than 150 times, and this is the result. I think it was totally worth it. All of these components are mounted on a steel chassis. There are 2 parts of it, a front panel and an internal support. As usual, we had both parts laser cut from steel, bent on edges and then finished with durable powder coating. But that was still a half of a job, because there must be inscriptions. Here I decided to again use dry transfer fonts. Those are such thin symbols attached to a film, so when you press on the film, they firmly stick to the surface. It looks to me that on the original panels, actually the labels were rather handwritten. Dry transfer letters take a lot of effort to position them, but I guess the result is much cleaner. And this is what we got. These panels will be positioned in the outer housing, which we made from 1.5mm steel. I must say that on the original request device, the connectors are located below the keyboards. That is not very convenient for us, so we decided to move them to the rear. So one will be for power and another for the displays. Next, using some dry transfer fonts, we added the labels for switches, and the switches and buttons in this section are exactly the same types used in the original console. Some are latching, some are momentary, and some have 2 or 3 positions. As I mentioned in the previous episode, technically the keyboards are the same at the control room and in SKALA engineering panels. And we went for engineering version because it takes less space. Those extra switches on it I used to control the SKALA mnemonic display we built in the past. Alright, so I made a quick check, everything fit well, so I could start installing smaller parts. The switch blocks must align precisely with the openings in the upper covers. That's not really easy to design that very precisely, so instead we made slightly elongated mounting holes in the chassis. And once this was done, I could finally attach the button caps, and honestly I was really excited to see the keyboard slowly appearing in front of me. And before we installed them inside the housing, I needed to make a few more things. First, program indicators, because they are the only components secured directly on the front panel. In the original console, inside were small incandescent lamps covered with lenses. The cool thing, however, it is possible to install instead warm white LEDs. It will look the same, but will consume significantly less current. Next, we needed to reproduce the error and attention indicator, and that was kind of a tricky one. Because the original was electroluminescent and manufactured specifically for SKALA. And so out of options, as usual, we made one from scratch. So first I printed the housing on a 3D printer. The original indicator glowed beautiful turquoise color, so to match it I used a method that we used before. There is a non-transparent mask with symbols, and then beneath there is a diffuser, and below that there are two addressable LEDs, one for each symbol. Everything is held together with sealant and secured using 4 screws. So this what it looks like after installation. Then I wired the keyboard switch blocks. The original keyboards are electrically arranged as matrices, so first I created common electrical lines for all button columns. Later I also added the lines for the rows, but in that moment I just didn't want too many loose wires getting into the way. And then these complete assemblies went inside the housing, and I began securing them with nuts on the mounting studs. Well, very soon I discovered that those studs had apparently been overheated during powder coating. They had become extremely fragile and just cracked. So eventually I had to find another solution and placed those enormous washers. Well, not elegant, but indeed very effective. All those controls are connected to a single ESP32 microcontroller. It doesn't have enough pins to handle entire keyboard matrix, so extended it using 3 GPIO expanders. I will be honest with you, that was mid-April, and the exhibition dedicated to 40th anniversary of Chernobyl disaster was approaching really rapidly. So I had almost no free time left, and I had to skip filming the process and instead managed to complete everything in just 3 days. So here is the finished result, but here we can see everything. So the keyboard switches are matrices, so there are those lines for columns I showed before, and also I added lines for rows. The difference between them that each switch in the row lines is connected through a diode, in a similar way how it was done in the original keyboards. That's actually very important, because when buttons change, for a moment the matrix can produce some false signals. So all this wire mesh eventually reaches the GPIO expanders, and some pins here are used for rows and some for columns. But as you can see, there are some free pins. That's because for now I didn't connect the upper row of switches used to control the SKALA mnemonic display. The reason is simple, I simply want to finish keyboard functions first and only then move to peripherals. And by this similar reason, for now I left disconnected the program selector, so the controller basically assumes there is always program number 8. That's the one which manages communication with the MTK display. And here we come to our fresh upgrade. A few details if you are first time here. So these round displays are called mnemonic displays of the reactor channels, or MTKs. And their function comes from their name. Put simple, on them light up the marks of reactor's channels which match a chosen condition. And on each square there are written coordinates of corresponding channel, so operator can visually assess a situation inside the core. Then, if they need, using those coordinates, they can type here request to see more information. But what to show exactly on mnemonic displays in the first place, you specify here by typing special codes or numbers. In our console, the controller has a big built-in database of all kinds of channel parameters. Well, for now it is static, but later it will be dynamically changing. So, when you type here something, the system generates a list of channels and sends it using the UART to this tiny board. That's a separate controller that has a VGA output, so we could connect a display to it. It can provide us with 1024 to 768 pixels image with 4 chosen colors. The board unpacks the data, draws the channel matrix, and on the right we have indicators of what is being displayed. On a real MTK, these indicators are in the upper right corner and they also glow. Okay, let's try some examples. So, there are 4 subprograms which are initiated in the same way. For them you press M here, and here you select the main program, 4 or 8, for indication on the MTK. Now, on this keypad we type 0 plus 3 zeros 1 and press start. This combination will show you all channels where coolant flow rate is lower than it should be. Then, if I type 0 plus 3 zeros too, I get a similar data, but opposite. This will be channels where coolant flow is too intensive. For each particular channel, the minimal acceptable flow rate may be different, depending on the position in the active zone. So the system compares the actual values with set point for each single channel and gives this combined picture. Next, if I type 0 plus 3 zeros 3, that will be all channels where temperature of gas mixture is too high. The difference that here the set point is one global for all channels. And finally, 0 plus 3 zeros 4 will give you all channels where boiling crisis margin is too low. What is that I explained in previous episode, so to be very short, this margin is a special number that indicates how close the channel to dangerous overheating. Now, there are more functions. For example, you can compare some parameter of the channel with a chosen number and show all the channels where parameter is higher or lower than your input. So, for instance, you remember that absolute maximum of power for a single channel is 3 MW. And during normal operation it must not exceed 2.93. Now let's imagine I want to see all channels where power is very close to that. So I type here K0N 4 zeros, the power of all channels. Then I press parameter and here I need to enter plus 2.92. But how do I do this on this keyboard if it doesn't have a decimal separator? You do it this way, you enter here 0 to 92 and then I press here 2, which means a magnitude, basically the position of the point. And then, using the sign plus or minus, I define the comparison. Here I want to see greater or equal to 2.92, so I press plus. And now when I press start, I get this. Once more, here is a dummy data, convenient for debugging. In real situation it will look different, but the principle will be the same. So, the system actually makes a lot of calculations for each channel, and when this quantity is big, that takes some time. So I programmed this indicator to light up until that calculations are done. That's very convenient, because now we can clearly see when we can send the next request. Such a computing-consuming yet very important thing you can do here is this. So, you can indicate the channels where a value of the chosen parameter is greater or lower than a chosen set point for that value for a chosen percentage. Yes, that complex. So, you may remember there can be two warning set points, low and high. The value should not exceed them. And there can be also two emergency set points, high and low, that the value must not exceed. So, in this case, on the left keyboard you enter the code and select one of four set points. And on this keyboard you select plus for greater or minus for lower. And then you always type 3 zeros, and the last two digits is that percentage. So say I want to see all channels where power exceeds their warning high set point, which is 2.93 MW for 2%. And this is what we get. So there are a few more functions, such as indication of channels with extreme values, but honestly I would like to learn a bit more about them so we can implement them correctly. That's a big work ahead, and of course I do not aim for 100% accuracy, but honestly even now it's really exciting to do it. And of course at some point I will make it open source so you can build it yourself. For now, as usual, updates on this and other our projects you can find on our Patreon page. The link is in description below. Your support helps us bring Chernobyl history back to life as it was never done before. Thank you for watching, and we will see you in the next one.